Clementin Boittiaux. He's a PhD student at Ifremer in France, and he's working on visual localization for underwater environments. And he's going to present his work from his PhD and also from his latest contribution on absolute pose regression.
Yeah. Thank you, Asia. And I'll try just to, okay, let's go. So, yeah, I'm doing my, as Asia told you, I'm doing my PhD at Ifremer, which is the French Institute for French National Institute for the Ocean Research. And they opened the PhD position about just in general localization for autonomous underwater vehicles in a deep sea environment. And so the task that I've been given and the task that we are studying is basically we have an autonomous underwater vehicle right here that just get to dive at a depth of between 2,000 and 6,000 meters. And on this depth, using current localization system, underwater localization system, you have an uncertainty of approximately 10 to 30 meters, depending on the distance between the robot and the ship. And usually this position uncertainty is also bigger than the site of interest that we want to explore. So it's a big problem, and we want to have a more accurate localization of our vehicle. So we have a lot of tools on underwater vehicles to achieve this. Basically, the main tool that will help us in this application is the USBL and other acoustic positioning system. So basically, the USBL just localizes the robot with regard to the ship, and then the ship is localized with a GPS, and we can just infer the actual latitude, longitude, and depth of the vehicle based on this sensor. So it gives a very coarse position of the robot. And then this position is refined using other sensors like an integrated INS, and also by integrating a Doppler velocity log, which gives the vehicle's, which estimates the vehicle's velocity with relation to the seabed. But you also have, for example, a pressure sensor that can give you the relative depth of the vehicle, but it's always relative to the tide. So you have to get a pretty good idea of where the tide is to get your actual depth, if you don't want to be a few meters away from the actual depth of your vehicle. So in order to solve our problem, if we want a really accurate visual localization, if we want a really accurate localization, which is what we are aiming for, we are focusing on exploiting the vehicle's visual observation to localize it in a more accurate manner. Because all of these acoustic sensors that cannot allow they only allow coarse localization with regards to the results observation. So let's step out of the water for a few minutes, and I'll just talk about the problem of visual localization in a more general manner, and how we added one of the main contributions of my PhD. All right, so visual localization is basically you have like acquired a bunch of reference images from a site of interest. And later you want to come back to this place, and just given one query image, you want to localize this image. You want to know where the image was taken. But following this question, you might ask, with relation to what do we want to localize? We have to build a reference model in order to localize with reference compared to this reference model. So there are several ways to build ground truth using these visual observations. You have several ways to get a ground truth for the poses of previous observation of your site. So one of them is structure from motion, which is just triangulating the observed points in different images to recover both the structure of the scene and the poses of the cameras. Another one of them could be RGBD SLAM if you have a depth sensor. But you also have, in some rare examples, motion capture system, which can just triangulate points given a set of cameras to give you an estimation of the position of tracked points in this frame. And you also can, for example, use gantry robots with a known odometry, which can give, for example, if they embed a camera, you could have the relative position of the camera, the absolute position of your camera in all views. So let's imagine that we have built our ground truth, in this example with a structure from motion. And then we have our ground truth reference model along with all the poses of the camera that we computed using structure from motion. And so whenever we acquire a new query image of the same spot, we want to actually estimate the pose, the 6 degrees of freedom pose of this camera with relation to every other pose and the reference model that we just did. So this 6 degrees of freedom pose of our camera, it consists of translation and rotation components, and it can be a little bit tricky because rotation and translation are not in the same space. They are in a Lie group called Special Euclidean group. Dimension 3, SE3. And so for this particular application, we targeted the neural network that learned this pose end-to-end directly from an image. So basically, we have a very simple setup where we just have an image as an input to a convolutional neural network, and we directly predict and estimate pose just based on this image. So the core idea, the core component behind this network is how do they learn the pose? We have to embed this pose difference between the estimation and the ground truth that we have. We have to embed it into a single scalar described by a loss function. So we want to describe pose difference in the SE3 manifold into a single scalar in order to make the network learn. So we'll go over a few of already defined loss functions for this task. So with this neural network architecture came the first loss function that was used to describe this pose difference. So this is PoseNet loss function. It's basically weighting the Euclidean norm between the two estimated translation, and is doing weird Euclidean distance between the quaternion, the rotation represented by quaternion between the estimated and the actual ground truth pose. There are several problems with this loss. One of them is that this does not relate to any intuitive geometric phenomena, the Euclidean distance between the quaternion. Also, the beta factor here is the same for all images. It's not obvious because it has to be determined through trial and error. And also, we still have the same problem is that rotation and translation are not in the same group, and we're just adding them in the same loss function. So to cope with some of this concern, DSAC uses a different error. So it just takes the maximum between the rotation and translation components. So it basically solves the weighting component, and to do that, it expresses the angle between the two quaternions in degrees and the Euclidean distance between translation in centimeters. But we still have a lot of problems with regard to the previous loss. It's still a bit of an arbitrary weighting factor, and the weighting factor is still the same for all the images, and it's still the same problem. It's not in the same group. So also in another paper, the authors of POSNet proposed to learn the weighting parameters to implement the learning of weighting parameters inside the loss function. And what we'll be mostly interested in is the geometric reprojection loss function, which was also proposed by the author of POSNet. Basically, you want to minimize how each point of the 3D scene reprojects into your ground truth camera view and make the distance between the reprojection of these 3D points in your camera, in your estimated camera view, and in your ground truth camera view. This implicitly solves the problem of weighting between translation and rotation. And more importantly, as pointed out by recent work by Bachmann and Al, it might be an optimal solution because for structure for motion based reference model, because it minimizes actually the same error as bundle adjustment. But there are still some problems with this loss function, is that it is poorly adapted to deep learning because it heavily relies on initialization, and mostly, so here we have the estimated, here we have the estimated camera, we have the ground truth camera, and we want to reproject all observed points in the blue cone into the image plane of the estimated camera, and there are a lot of problems with that. So all green points, they are projected into the minima, into the global minima, but all black points, for example, are projected backwards and lead to another local minima, which is like the exact inverse pose that we want to play. And all these red points here, they project to infinity, which causes this geometric projection loss function to have two problems. One is that it is not defined in this space, and it has also a wide local minima that is just as wide as the global minimum. So we need a way to solve this. And actually, we want to find a loss function that is able to overcome both of these problems by just getting to approximate the geometric projection loss function whenever it's close to the optimal solution, but which can just get rid of the non-differentiability of the function, as well as getting out of this local minima zone. So in order to do this, we have our 3D scene, our ground truth camera in blue, and our estimated camera in orange. And what we do is we actually replace these observed 3D points that we reproject into each view. We replace it with planes. So these planes, they are parallel to the ground truth image plane, and instead of reprojecting points into each views, we actually express the error directly in the homographies induced by this plane between these two views. So instead of relying on points, we will say like this point is not a point, it's a plane, and this plane we want it. We define the error of this plane as the Frobenius norm of the difference between the homography and the identity matrix. Because when poses are superimposed, the homography should tend to the identity matrix. And what we do once we have that, in order to take into account all points in the scene, we integrate these planes between the maximum and minimum distance representing the scene. And there is actually a closed form solution to this problem that only relies on rotation in translation components, as well as the normal vector and the minimum maximum distance of the scene. And the normal vector, we just fix it to be 0, 0, -1 so that each plane faces the ground-truth camera image plane. We actually make a link into our paper as to how this loss function approximates the reproduction error as poses become closer. And we also demonstrate that it reaches its minimum if and only if poses are superimposed. So here we show an example of a pose that is initialized backwards, and we minimize the reproduction error. And as you can see, the pose will converge to its to the local minima that we described above, and just be in the complete opposite direction as a ground-truth pose. And here we show the presented homography-based loss function, which just kind of gets out of this minimal very quickly and approximates the reproduction error as poses become closer. So some results on the King College scene, which is the structure for motion based. We have better reproduction error than PoseNet, but worse than the geometric reproduction error. Whether on RGBD based reference model, we actually outperform the geometric reproduction error. So these results, they are consistent with the claims of Parkman and al. That is that we cannot perform better than the geometric geometric reproduction loss, because it minimizes the same on structure-based reference model, because it minimizes the same error. However, on depth-based approaches, we actually do perform better because we directly have access to this depth information that we rely on for our loss. And even though we don't minimize exactly the same error, it's still better than the geometric reproduction error, which minimizes is not clearly the error that's minimized during depth-based time.
Oh, question.
Yeah.
So you said that your loss is approaching the geometric loss.
Yeah.
The horizontal loss.
Yeah.
So then you should achieve the same performance.
Yes. So it approximates the geometric reproduction error as we get closer, but during the optimization, the poses are never close enough to the ground truth, so that it can it approximates, but it's not exactly the geometric reproduction error. I mean, it's exactly when poses are completely superimposed, but whenever you have a slight difference, it's not completely the geometric reproduction error, so it can't reach the same level of accuracy.
Okay.
It tends to the geometric reproduction error, but it's still, if there are a small error, it's not quite exactly the same for this.
So your approach will converge to the correct solution, but
Yeah.
it will be exactly the same.
It's not exactly the same one. Yeah.
So if you would switch at the end of the optimization, you would switch to geometric.
It would be smart to, for example, initialize. If we have, for example, a structure for motion based reference model, it would be smart to initialize with our loss function so that it's clearly in the right basin of convergence, and then refine using the complete geometric reproduction error, or just completely redefine the function so that it switches from one error to another when their poses are really close. But we would have to do this in a differentiable way, and it's the tricky part.
There is a question also on the chat.
Maybe
you can read it.
Maybe I can read it.
Okay, I think it is.
Okay.
So you show how the homography loss helps with this space where there is no convergence.
Yeah.
And then person asked, how does the homography loss helps with bad initialization? Can you explain this in more detail?
Yeah. So basically, even in the case of bad initialization, I mean, the approximation that we are doing in our homography-based loss function is that we are actually discarding regarding the last row of the homography matrix. So we are completely discarding this projective geometry element. And we don't have any problem when the poses are completely wrongly initialized, because we will completely disregard this I don't know how to say this, but yeah, basically we can converge even if we are poorly initialized, because it's expressed directly in the homographies, and this loss function here for the Venus norm of identity matrix minus H. I mean, I would have to show the paper. I mean, if there is time, it will be okay.
The homography projection always means something, even if you're wrongly initialized, or the projection matrix, it can become degenerate if it's wrongly initialized.
No, you can initialize like it. You can initialize it completely randomly, because I mean, when you're very far from the ground truth camera pose, it really has nothing to do with like the geometrical projection loss. It's really far from it. It just only converges when you're really close to it. But else, it's just really a way to weight rotation and translation without having to deal with these weight rotation and translation based on the distance of the scene. But when you're far from the ground truth, it completely alleviates this problem. And whenever you get close, approximate, whenever you get far, it's like very far from the geometrical projection error. So you can just initialize it completely randomly, and this is one of the big improvements with regard to the geometrical projection error, is that you don't have to initialize in importance.
I think this answers the question. As, the chat will make this.
All right. Okay, so let's get back to our underwater world. And so one of the first problems that we have is that there are currently absolutely no datasets for underwater visual localization. So we had to build one, and the data is very expensive in these settings. So you could guess it's a few hundreds of thousands of euros of acquisition. And we have the 4 dives on the same hydrothermal chimney lying at a depth of approximately 1700 meters. And these 4 dives occurred between 2015 and 2020. And they always occurred on the same hydrothermal vent, and we were able to recover approximately 5,000 images per dive using different sensors and always in different water conditions. We also have access to previously mentioned navigation data to help with our reconstruction, with our suite of promotional construction, which give us latitude, longitude, and altitude information for our robot at a frequency of 1 Hz. But these navigation data, they are only consistent within the same visit. As I explained before, because we integrate INS and anything, it's fine to rely on these navigation data in one visit. But if you want to compare this latitude, longitude, and altitude information with the navigation provided by another visit, it's absolutely not comparable. You might have an offset of 10 to 30 meters. Yeah.
Do you know what's the width of this navigation system in the INS?
I have absolutely no idea of the order of magnitude, but it's trustable enough so that you can really like I mean 1 hour, I think it's enough so that you fall back, because you even if you have INS and everything that only relies on the integration of the sensor, you also integrate the USBL, which gives you like, it's just like a GPS. So you always have into your Kalman filter this absolute pose that you can always use to correct the actual position of your robot. So it reduces drift by a lot.
Okay.
No problem. So we have to build the ground truth. We don't have a lot of options. Motion capture and RGBD motion capture is out of question. We don't have a gantry robots at this depth. RGB slam is way harder to manage in underwater settings because of the absorption of the infrared light. So we have to rely on a reference model based on structure promotion, but we have another problem is that these are environments that are really different from the one above water, and most classical computer vision algorithms, they are not used to the sources of variability that can occur in such settings. So, for example, if we just naively apply SIP to an underwater image of different visits, we have like absolutely no correct matches between the two images, even if we filter it with an estimation of the essential matrix. So we benchmarked several feature matching algorithms, and the problem was actually very quickly solved by superpoint plus superglue that shows exceptional generalization to these underwater sources of variability. So problem solved, but we still have to decide which images of different years to match together. And for that, we have to rely on global retrieval algorithm. On these, we did not find a proper way to implement these in our setting. We tried traditional approaches like bag of visual words on a set of different features, and it didn't work. We tried NetBlad on other global retrieval network. It didn't work either. So, for example, here we have a figure illustrating the query image in green. And all the image retrieved by the NetBlad network are in red, while all of the possible candidates that it could have retrieved instead are in blue. Yes.
You have to be fine-tuned superpoint.
No,
is that
not
out of the box work?
Yeah, out of the box it works. And so this is the only proper underwater data that we have, like in great shape, like. And before this, we could not even fine-tune superpoint because we did not have the data to do this. So this is really the problem with Torsten and Asia. We worked on fine-tuning NetBlad on this data, and it actually shows to improve a lot the localization accuracy. But prior to this dataset, we did not find any proper underwater dataset that could help us to achieve such fine-tuning. So NetBlad, superpoint and superglue work really great even without fine-tuning, but all other networks they just completely fail. So we had to adopt a specific structure for motion pipeline to make sure that we could match images of different years within the same reference frame. So basically we just built each model individually, like for each visit year. Then we perform similarity registration using the teaser++ model to get a coarse estimation of all poses in the same reference frame. And then we used all these poses in the coarse reference frame to match images between different years. And then we were able to run bundle adjustment from scratch using these matches to get a final model that just triangulates points of different images of images of different visit years to get an accurate structure for motion reference model. And finally, also, we have to retrieve the scale of our model. So it's a simple application. We just use the Omiyama's algorithm to align the poses of our estimated structure for motion model with the navigation data that we previously talked about. But we have to use the navigation of that have only 1 year, because, as I said before, they are not consistent within different years. So a bit of analysis of this underwater data and why it should interest the people in this room that are doing visual localization. We are going to talk about the challenges. You see here an image of the same place on the hydrothermal vents that was taken in 4 different years. And you see that there is a heavy growth in mussel population that significantly alters the visual aspect of the scene. And because of this growth, there are no real matching 2D to 2D points between these two images. And this results, for example, in our final superposition, this results in very scarce cross-year matching in the structure promotion. So on this part of the model, the poses have to rely on images of the same year to register properly. But we have to find algorithm that should be robust to perform 2D matches, for example, between these 2D image. And maybe dense applications might be more robust to this kind of problem. Another problem is whenever the structure gets destroyed. For example, here you can see a part of the hydrothermal chimney that was shot by the robot at the end of the 2015 dive. And so it's completely lacking in the other year, but also you have, for example, additional geometry. For example, they put thermometer. Yeah. Temperature sensor on the chimney, and if you look at it really close, it's in some images, it's the only information you have to actually localize yourself. I did not mention it, but so this vent here is approximately a bit more than 15 meters high here. And the total covered area is about 800 square meters. So you might think that it's small given the presentation, but it's actually a really big infrastructure edifice. So if you want to try it on your data, it's available on the marine data portal, which is called Sinoe. And there will be a paper released in, I guess, a few weeks or a few days on arXiv, and hopefully in the journal in a few weeks. Let's completely switch to another topic, which is the recovery of color of underwater images. As you might have seen from the images that I've shown to you in this presentation, you might notice that there are the color and appearance of underwater images completely rely on the position of the camera with relation to the scene. And in visual localization, this is a big problem because we don't want the appearance of our scene to change just because of the position of our camera. So we came up with a method to correct these phenomena induced by the underwater medium. So if we want to summarize a bit what I just said, underwater color restoration, it's the problem of retrieving the color of the acquired underwater image as if it was captured in air. And actually, all our work relies on a model, on an image formation model that was developed by Akenak and Al. And this is an approximation to a more accurate physical model for light propagation in underwater mediums. And so basically, Akenak and Al, they proposed a method to both estimate the parameters of this model given an image and its distance map, and then to inverse this model to recover the colors of the image as if it was taken in air. So we describe this model shortly. So this is only the simplified model. We have our acquired image entity in underwater settings, which is called I. So this is the acquired underwater image. J is actually what we want to retrieve. it's the restored image. So it's like the original albedo of the scene. And what we say is that this pixel intensity in the acquired image is equal to the actual albedo of the scene multiplied by a term that is dependent of the distance to the scene and which relies on which actually attenuates the color signal which actually attenuates the pixel intensity based on the distance to the scene. And you also have this term here, which is called backscatter, which is basically how much of the light that your source of light emits is refracted back into your sensor. And it's actually composed of the veiling light B and another backscatter attenuation signal, which we call gamma. And if we want a closer look into these parameters, right now I can explain to you, for example, B, the veiling light, is the blue at the infinite distance that we observe in underwater image. For example, in this image, it will be like the bluish part of the image where really you don't see any structure. So actually, estimating the parameters of this model given only one image and one distance up is underdetermined problem because you have as much observation as you have pixels, but you have the same amount of parameters. You have J parameters, but you also have 3 parameters for the model. So you have J plus J observation and J plus 3 parameters. So I will explain, I detail a bit the model that we've just seen. So for example, in here, you can see that B will be what will be tending. So this is a plot of image intensity versus the pixel distance. And so basically what we can see is that at a certain distance, all pixels will tend towards the same color, which is B. And this is the backscatter of the image. Basically, it tells that this pixel intensity, they will tend towards as much as pixels are observed in far elements of the scene. Their intensity will be adding more light will refract on the sensor, and there will be a shift in intensity based on this refracted light. But also, as pixels go far and far from far furthest away from the scene, there will actually be relative elements of the water that just completely absorb the color intensity of the pixel. So you have both elements here on the bottom, you have backscatter, in the top you have the color attenuation part of the water model. So what they do in see-through is that they rely on additional hypotheses to try to estimate this water model, the parameters of this water model, even though it's an underdetermined problem. So basically what they do is they say, okay, if J tends to 0, it will, if you're observing a black pixel, normally you should have I that tends to this only backscatter coefficient here, dependent on the distance. So you could just hypothesize that at different distances to the scene, you will always have at least some black pixels. And so basically what you're trying to do is fitting these backscatter term based on the darkest pixel at each distance. So you get your backscatter estimation. And once you get your backscatter estimation, you can actually make an estimation of the illuminant map of your image without the backscatter term. And this illuminant map is directly related to the distance because of the phenomena that we just explained earlier. And we can actually estimate the color attenuation coefficient based on this estimated distance, based on the estimation of the illuminator. So with this method, using only one image, you can reach this kind of results here. So you see that the reddish part is already so close to the scene, so it doesn't have many changes. For example, you remove the blue of most of the center part of the image, but in the very far part of the image, you don't have enough information in the remaining 8 bits of your image to actually retrieve proper information. So this is why you're mostly observing noise in the back of the image. So based on these limitations, we had one simple idea. So since we are doing a structure for motion on underwater scenes, we can actually leverage multi-view information to try to make this, to shift this problem from an underdetermined problem to an overdetermined problem, where we could have, for example, observed multiple points of the same points of the scene at multiple distances of the scene. And so we are able to correctly track the pixel intensity at different distance and estimate the underwater image formation model that we were talking about earlier. So basically, what we do is that we just first built a structure for motion of the scene, and then we built a 3D mesh based on the structure for motion. From this mesh, we can build depth maps, and we can project points between one given view and every other view. We can match points in one view with points in every other view using the camera pose that we have using structure for motion and the depth map that you just estimated. So basically, we are doing very, very dense matching using depth map on estimated camera poses. And the advantage of this matching method is that we can also match points in areas where we have very low contrast. Once we've done this, once we have multiple observation of the same point at different distances, we can just express the same model as before, but in a multi-view setting, where we just define the I parameter additionally, and we say just that the J, the retrieve albedo of the scene must be the same in every image that observes the same 3D point, but its intensity changes depending just on the viewpoint. And then we just estimate the parameters of the model, including the restored image in a least square setting. And we found that there is actually a closed form solution for the J and B parameters. But this closed form solution is still dependent on the beta and gamma parameter. But I'm not going to detail the computations here. So basically, differences here, you can really see an improvement in the background of the image, because we have multiple views of this scene at closer depths. And then we are able to virtually increase the dynamic range of the image to retrieve these pixel intensities. And so we also show results in short videos. So our approach is on the top right. I have several to really make our point. So as you can see, they are really we are really recovering all the actual colors of the pixel that could not be retrieved using only one single image, because there will not be enough information in the single image to retrieve these colors because of the 8-bit quantization. And that's it for me. If you have any questions, feel free to ask.
There's another question from
Yeah.
the chat. have you thought about recovering color on the 3D surface and then rendering the resulting model
Yeah, of course. So
to the third image?
yeah, so but basically what we did is we did one approach, which is to render to texture the 3D model using corrected images and then render the 3D model. So it gives very similar results, except that in our approach, if we only take the resulting image, we have really one pixel. Each pixel has its restored color, whether in if we render the textured model, the texture will not have one corrected pixel. Each pixel will not have its according really 3D point texture color. Basically, your texture model, sorry, I'm having trouble to make that point. Your texture model, in the model of your texture, you don't have one texture intensity per pixel in your render image. So it's you have to interpolate texture intensity in your final render image. I don't know if it's clear.
Yeah, so you mean the figure of the warping.
Yeah.
So if you do the inverse warping thing, then it solves the problem. So instead of projecting, you go from the image to the rendering and then you get it. So then you will have a color for each pixel.
But you have in your texture map, you will have to get exactly one pixel per. You have to get a texture map that is as wide as one pixel for each of your pixels in your rendered image.
And this is not the
This is the case if we only do this dense projection thing, but if we really like completely render, render a complete 3D model, we cannot have a texture map that is that large. But it's actually some work that has been done by Kevin Keuzer's team at Guiomar, and they do differentiable rendering using similar-ish model for deep sea, and they basically directly correct the texture map of the model from multiple observation of an underwater scene. And they do this with differentiable rendering using the Mitsuba 2 framework.
Okay, I'm sorry. So we said, I meant that you directly optimize the texture of the model instead of recovering the images and then texturing. The difference is where you recover the original signal in the original images or in the 3D structure. But I think maybe that's the answer.
Yeah.
So it's more about, so do you correct the color of your 3D mesh model?
Yeah.
Then project it onto the images?
Yeah. No.
Versus, so that's the question. Why don't you do that instead of correcting the images? Yeah. Directly. Why don't you correct once and for all the 3D model with all of your information?
Yeah. And then because we wanted so texture map has a finite resolution, and we wanted in our image to get exactly one pixel, the pixel-wise resolution of our image, of final acquired image. So if you render, for example, a texture model using these, if you render a texture model, you will get, you have to interpolate the colors of images between the texture patches that you have. Whether with this method, you really like implicitly have one pixel, exactly one pixel has its own restored color. You have a full resolution restored image without interpolating any of the texture map that you have, or you will have to get like an insanely huge texture map to get the same results.
Okay.
This is the main difference. It's really in the limitation of the resolution of the texture map. But then you could argue that you could do exactly the same thing using, for example, instead of relying on texture map, you would optimize vertex colors and do the interpolation, and it would actually very probably lead to the same result as we do, because we rely on the texture and the mesh to perform this depth map estimation. So if instead of optimizing directly in the texture map, you will optimize directly in the vertex color space, I think you will get closer results to what we obtain, but it's still we went that way because also it was already in the pipeline. This is the first thing that we thought about, but there is definitely, I think it's in the future, for future work, it's much more interesting to think in terms of render the differentiable rendering and render models and NeRF models, implicit neural scene representation.